Let little f be the continuous function defined on the closed interval -5, 8, whose graph consisting of 3 line segments and a semicircle centered at 4, 0 is shown below. Let capital F be the function that is defined by capital F of x is equal to the integral from 2 to x f of t dt. Find the x-coordinate of each point at which the graph of capital F has a horizontal tangent line. For each of these points, determine whether capital F has a relative minimum, relative maximum, or neither a minimum nor a maximum at the point. Well, by the fundamental theorem of calculus, capital F prime of x is equal to little f of x, and that is 0 when x is -2, 2, and 6, right? Because this is the graph of little f. So we could just look at where it hits the x-axis to see where little f is 0. Capital F prime, which is equal to f, changes sign from positive to negative at x equals -2. It's above the x-axis and then below the x-axis. Therefore, capital F has a relative maximum at x equals -2. Capital F prime equals little f changes sign from negative to positive at x equals 2. It's below the x-axis and then it's above the x-axis from left to right. So therefore, capital F has a relative minimum at x equals 2. And at x equals 6, little f, which is the same as capital F prime, does not change sign. So f has neither a relative minimum nor a relative maximum at x equals 6. Let little f be the continuous function defined on the closed interval -5, 8, whose graph consisting of 3 line segments and a semicircle centered at 4, 0 is shown below. Let capital F be the function that is defined by capital F of x is equal to the integral from 2 to x little f of t dt. For x between -5 and 8, find all values of x for which the graph of capital F has a point of inflection. Explain your reasoning. Well, we could see it right here where I have circled x equals 0, x equals 4, and x equals 6. F double prime, right, capital F double prime, I should say, which is equal to little f prime, changes sign at each of these values, right? Because little f goes from decreasing then to increasing, and it's from increasing to decreasing, and then from decreasing to increasing. So since little f is changing between increasing and decreasing, little f prime is changing between positive and negative. Right? It's negative then positive, positive then negative, negative then positive. Okay? So that means that all 3 of those x values are where capital F have point of inflection. Let little f be the continuous function defined on the closed interval -5, 8, whose graph consisting of 3 line segments and a semicircle centered at 4, 0 is shown below. Let capital F be the function that is defined by capital F of x is equal to the integral from 2 to x little f of t dt. Find the absolute minimum and absolute maximum of capital F over the closed interval -5, 8. Explain your reasoning. Okay, so first of all, we have the critical points of -2, 2, and 6. And we also have endpoints of -5 and 8. So we're going to be checking capital F at each of those 5 points, and then just picking the one that gives us the biggest and smallest values. Okay? Capital F of -5 is, well, we're plugging a -5 in for x. So here goes the -5. So it's the integral from 2 to -5 f of t dt. Okay, so what I'll do here is just, we're going from 2 to -5, and since it's backwards, it's going to be negative, so we'll put a minus sign first, and then we're going to go in the forward direction because we put the minus sign to account for the fact that we went backwards. Now, we're going to be computing all the net area from -5 to 2. So first we have this trapezoid, which has bases 3 and 2 and a height of 1. So it's the average of the bases, 3 plus 2 over 2 times the height of 1. Then here we have a triangle and another triangle that cancel each other out. So this net area is 0. And here we have a triangle below the x-axis of base 2, height 2. So it's negative because it's below the x-axis, 1/2 base times height, 2 times 2. Okay. And 3 plus 2 is 5 over 2 times 1. That's just 5 over 2 minus these cancel and we get 2. Okay, so that's 5 over 2 minus 4 over 2 is 1/2. And there's still that minus sign in front there from when we reversed the direction. So f of -5 is -1/2. Next, f of -2, that's the integral from 2 to -2 at little f of t dt. We're going to reverse that direction again like we did in the last one by negating the integral. So it goes from -2 to 2 now. Right? And we can just go ahead and take the area of this. The base is 4, the height is 2, and we negate it because it's below the x-axis. So the two minus signs cancel each other out, and we're just left with 4. F of 2, this is an easy one. The integral from 2 to 2 f of t dt is equal to 0. No area is generated when you're going from one point to itself. F of 6 is the integral from 2 to 6 f of t dt. This is just the area of this semicircle. The radius of this semicircle is 2, so it's pi r squared, pi times 2 squared, but it's only a semicircle, so we divide by 2. So that's 4 pi over 2, which is 2 pi. And f of 8 is the integral from 2 to 8 f of t dt. Okay, we already did from 0 to 6, that's 2 pi, and now we just have to add the area of this little triangle here. That's 1/2 base times height, 1/2 2 times 2, so that's 2 pi plus 2. Okay, we're almost done. The absolute minimum of capital F on -5/8 is f of -5 equals -1/2, simply because that's the smallest value that appears here. It's the only negative one. And similarly, the absolute maximum, we just take the biggest value. Well, 2 pi is about 3 times 2 is 6. It's a little more than 6. So 2 pi plus 2 is a little more than 8. So that's going to be the largest one. Let little f be the continuous function defined on the closed interval -5/8, whose graph consisting of 3 line segments in a semicircle centered at 4, 0 is shown below. Let capital F be the function that is defined by capital F of x equals the integral from 2 to x, little f of t dt. The function g is defined by g of x equals the ln of capital F of x over 2x. Find g prime of -4. Okay, so we need to do a chain rule here, right? The derivative of ln is the reciprocal of this. Instead of writing 1 over f of x over 2x, which is a little messy, I'm just going to flip the 2x and the f of x. And then we have to take the derivative of this, which is a quotient rule, denominator, 2x, times the derivative of the numerator, capital F prime of x, minus the numerator, which is f of x, times the derivative of 2x, which is 2, all over the denominator squared. 2 squared is 4, x squared, x squared. Okay, so we want to compute g prime of -4. So let's see, 2 times -4 is -8. That's over capital F of -4. Again, 2 times -4 is -8. F prime of -4 minus 2 times f of -4 over 4 squared, 16 times another 4 is 64. All right, so we have to figure out what capital F of -4 and f prime of -4 are. Well, capital F of -4 is the integral from 2 to -4, little f of t dt, which is the negative of the integral from -4 to 2f of t dt. When you switch the limits, it negates the integral. The reason we did that is so that we could go in order from left to right, which is much easier to visualize, because now we could just think of it as the net area. Okay, so we're going to split this into two pieces, from -4 to 0, and then from 0 to 2. From -4 to 0, we just have a positive area and a negative area, which cancel each other out. Those two triangles have the same area. And then we just have to compute the area of this triangle, which is 1/2 base times height, 2 times 2. So that's 1/2, 2 times 2. It's below the x-axis, so it's negative. And we're going to multiply that by the negative from before by reversing the direction of the integral. So that just becomes 2. Now, capital F prime of -4 is equal to little f of -4 by the fundamental theorem of calculus. And little f is what this graph is of. So we could just look at the graph to figure that out. So little f of -4 is 2 because the point -4, 2 is on the graph. All right, now we're ready to plug these values in. Capital F of -4 is 2. So we put a 2 there and a 2 there. And Capital F prime of -4 is also 2, so we're going to put a 2 here as well. And that comes out to 5/4, or as a decimal, 1.25. Let little f be the continuous function defined on the closed interval -5, 8, whose graph, consisting of 3 line segments and a semicircle centered at 4, 0, is shown below. Let capital F be the function that is defined by capital F of x equals the integral from 2 to x little f of t dt. The function h is defined by h of x equals little f of 3x squared minus 2x over e to the x minus 1. Find an equation of the tangent line to the graph of h at the point where x equals 1. Okay. So, well, first of all, h of 1 we get by plugging in a 1 for x. So that's f of 3 times 1 squared minus 2 times 1 over e to the 1 minus 1. So we get 3 minus 2, e to the 0. So 3 minus 2 is 1, e to the 0 is 1. So that's just f of 1, which is -1. We could see that right from the graph. This is the graph of f, remember, little f. So 1 comma -1 there. Okay. Now, h prime of x is a chain rule. So it's little f prime of 3x squared minus 2x over e to the x minus 1 times the derivative of the inside, which is a quotient. So we'll have to do a quotient rule. Denominator, e to the x minus 1, times the derivative of the numerator. It's just power rules, 6x minus 2, minus the numerator, which is 3x squared minus 2x, times the derivative of e to the x minus 1, which is e to the x minus 1. Technically, there's a little chain rule in there, but the derivative of x minus 1 is just 1. So it's not too critical. And then we divide by the square of the denominator. When you square e to the x minus 1, remember when you raise a power to a power, you can just multiply the powers. 2 times x minus 1, you could distribute as 2x minus 2. Or you could leave it undistributed. It's up to you. Okay. Now we're just going to go ahead and plug in the 1. Up top, we just get 3 minus 2, which is 1, over e to the 0, which is 1. So this just becomes little f prime of 1. A lot of simplification here too. E to the 0, 6 minus 2 is just 4. That's where this 4 comes from. 3 minus 2 is 1. E to the 0 is 1. So this is 1. And e to the 2 minus 2, that's e to the 0, which is also 1. So f prime of 1, if we look at the graph, the slope at 1 is 1, right? Rise over run. You can think of it as up 2 over 2, which is 2 over 2 or 1. Okay, so that's f prime. That's f prime of 1 is that. And this 4 minus 1 is 3. So as I've said, that's 3 times 1. The slope is 1 here. Okay, so that's equal to 3. And now we could go ahead and write an equation of the tangent line using point slope form. It's y minus -1 or y plus 1 is equal to the slope, which is 3 times x minus 1. Let little f be a twice differentiable function that is defined for all real numbers and satisfies the following conditions. F of 1 is 3, f prime of 1 is 5, f double prime of 1 is -2. F of 3 is 2, f prime of 3 is 1, f double prime of 3 is 0. Let B satisfy B is between 2 and 3, and let D satisfy that D is between 1 and 5. Explain why there must be real numbers A and C, with A and C both between 1 and 3, such that f of A times f prime of C is equal to B times D. Okay, so first of all, we're given that f is twice differentiable. So that means that both f and f prime have to be continuous. Right, because differentiability implies continuity. F twice differentiable means that f prime is differentiable, and therefore f prime is also continuous. And of course, f is differentiable, so f is continuous. Okay, since f is a continuous function, satisfying that b is between f of 3 and f of 1, right? B is between 2 and 3, but 2 is f of 3, and 3 is f of 1. So since b is between those two values, the intermediate value theorem guarantees a value a between 1 and 3, such that f of a is equal to b. Notice that in this case, the f of 1 is to the right of f of 3, just because that's what happened here, right? F of 1 is a bigger number than f of 3. The intermediate value theorem doesn't care about which one came first, whether the function is higher or lower at each of these points. It doesn't matter. It still holds. Now we're also going to apply the intermediate value theorem to the derivative, which is also continuous, right? Since f prime is a continuous function, satisfying that d is between f prime of 3 and f prime of 1, right? D is between 1 and 5, f prime of 3 is 1, f prime of 1 is 5. The intermediate value theorem guarantees a value c with c between 1 and 3 such that f prime of c is equal to d. And now we can just multiply these two equations, or more specifically each side. F of a times f prime of c is equal to b times d, which is what we were hoping for. Let f be a twice differentiable function that is defined for all real numbers and satisfies the following conditions. F of 1 is equal to 3, f prime of 1 is 5, f double prime of 1 is negative 2, f of 3 is 2, f prime of 3 is 1, f double prime of 3 is 0. Is there a value c for c between 1 and 3 such that f double prime of c is equal to negative 2? Justify your answer. Okay, so f is twice differentiable, which means that f prime is differentiable. And since differentiability implies continuity, then we get that f prime is continuous. In particular, f prime is continuous on the closed interval 1, 3 and differentiable on the open interval 1, 3. Right? So the mean value theorem guarantees a value c between 1 and 3 such that f double prime of c is f prime of 3 minus f prime of 1 over 3 minus 1. And now we just compute f prime of 3 is equal to 1. F prime of 1 is equal to 5. 3 minus 1 is 2. 1 minus 5, so that's negative 4 over 2, which is equal to negative 2.